Hi everyone, welcome back to Chem Help ASAP. Today we're talking about how buffers work and what is buffer capacity. Let's get started. Let's start with how buffers actually work, or what is the action of a buffer. So we know that buffers are solutions that resist changes in pH. How do they resist changes in pH? Let's dig into this a little bit. So in our first example, we have a buffer with hydrofluoric acid and sodium fluoride. We want to know what happens when some sodium hydroxide is added. So we already know that even though we're going to be adding a strong base to this buffer, it is going to resist that change in pH. But again, how does it do that? So the first thing I do is identify my acid-base conjugate pair in my buffer. And for me, the best way to do that is to write this equation right here, because then it becomes very obvious where my acid-base conjugate pair is. So when I add sodium hydroxide to the solution, I am adding both sodium ions and hydroxide ions. I don't really care about the sodium ions. They're just spectator ions. They have no acid-base properties, but I am very interested in my hydroxide because yes, that definitely has acid-base properties. So hydroxide is a strong base. If I am going to neutralize this hydroxide so I don't change my pH value, I need an acid to neutralize this base. Well, going back to my acid-base conjugate pair, which one of these is going to come and neutralize my hydroxide? Again, I need an acid, so I'm not going to choose my conjugate base. That's not going to neutralize another base, but my weak acid will neutralize my base. So my weak acid is going to neutralize my hydroxide, and it's just going to form water and a little bit more conjugate base. So even though we added some strong base to this solution, basically the hydrofluoric acid said, "Not today, hydroxide, I'm going to neutralize you." So what happens when we put hydrochloric acid in solution? Well, we form hydronium and chloride. Again, just like with my sodium hydroxide, I'm not so interested in the chloride. It's got no acid-base properties. It's just a spectator ion. But I am very interested in my hydronium because, of course, that is my strong acid. So if this is going to resist changes in pH, I need a base to neutralize this strong acid. Coming back again to my conjugate pair, I don't want to choose my weak acid. A weak acid is not going to neutralize an acid, but my conjugate base can come in and neutralize this acid. So my conjugate base is going to neutralize my hydronium. Again, it's going to form water and a little bit of my weak acid again. Remember how in our previous example, hydrofluoric acid said, "Not today, hydroxide"? Well, in this case, our conjugate base, our fluoride ion, said, "Not today, hydronium." This is why it's so important that buffers have an acid-base conjugate pair. You need both. Let's do this with another buffer. This time my buffer is with ammonia and ammonium chloride. What is going to happen when I add some potassium hydroxide? The first thing I want to do is identify my acid-base conjugate pair because that is where all the work happens. So here is my equation when ammonia is in water, and you can see its conjugate acid is right here. So here is my pair. I have a weak base, ammonia, and I have its conjugate acid, ammonium. So what happens when I have potassium hydroxide in solution? I get potassium cations and hydroxide anions. Again, I'm most interested in my hydroxide anions because potassium is just a spectator ion. So potassium hydroxide is adding a strong base to the solution. To neutralize that strong base, I need an acid. So looking back at my conjugate pair, I'm going to choose my ammonium cation because that is my weak acid. So my ammonium comes in, it is going to neutralize my hydroxide. As usual, it's going to make water and a little bit of ammonia. Now let's see what happens when some nitric acid is added. So when nitric acid is in solution, it gives us hydronium and some nitrate. Again, I don't care about the nitrate. It's just a spectator ion. I'm really focused in on this hydronium because this is my acid. To neutralize my acid, I need a base. So coming back up to where I identified my conjugate pair, my base is my ammonia, so it is going to come in and neutralize my acid. So here is my ammonia reacting with my acid. Again, it's going to form water and a little bit of ammonium. Once you do a couple of these, you start to hopefully see the pattern. If you're going to add a strong base to a buffer, you need to identify the acid in your conjugate pair to come and neutralize it. If you're going to add a strong acid to a buffer, you need to identify your base in your conjugate pair for that to come and neutralize it. Okay, here is our buffer. We have a 1 liter buffer with formic acid. It has a concentration of 0.250, and we have its conjugate base, lithium formate, again, 0.250 as well. So we have the same concentration of weak acid to conjugate base. We'll see how this is important later. We're also given the Ka of formic acid right here because we will need that as well. So initially, let's just find the pH of this buffer before we add anything to it. So here is our balanced chemical equation, again, in equilibrium. And just to point out, here is our weak acid and our conjugate base. I'm going to use Henderson-Hasselbalch to calculate the pH. Here's my generic Henderson-Hasselbalch. I'm going to change this over to my specific buffer. So here is Henderson-Hasselbalch with my specific buffer. Again, here's my formate and my formic acid. I also converted this pKa into negative log of Ka because my problem gave me Ka, not pKa. Okay, so at this point, I just need to plug my numbers in. So plugging in for my Ka, and again, my concentration of formate and my concentration of formic acid. The thing I want to point out is this term goes to 0 because, of course, the log of 1 is 0. So my pH is simply my pKa, which is 3.74. Okay, so let's take this buffer and let's add some strong base to it. And specifically, we're going to add 0.4 grams of a strong base, sodium hydroxide. Well, we know we're going to do some kind of stoichiometry, so I need to convert this 0.4 grams into moles. So let's do that first. So here's my 0.4 grams of sodium hydroxide, converting it to moles. I have 0.01 moles of sodium hydroxide. So that's how many moles of sodium hydroxide I'm going to add to this buffer, and I'm going to see what happens. So what is going on chemically here? I've added a strong base. It needs to be neutralized by an acid. Well, what is the acid in this buffer? Going back to your two conjugates here, my formic acid is going to neutralize. So here is my chemical equation of what happens when I add my sodium hydroxide. The formic acid comes in, it's going to neutralize my hydroxide, and it's going to form water and a little bit of formate. So how much of my formic acid is going to be used? I just need to do stoichiometry for this. So for all of my moles of hydroxide to react, I'm just using my mole ratio here. I'm going to use 0.01 moles of my formic acid. I do need to keep track of how much of my conjugate base I have formed, because I'm going to use up some of my acid and I'm going to form some of my base. So again, I just do stoichiometry. Taking my moles of hydroxide, using my mole ratio, I am going to form 0.01 moles of my formate. So my moles of my formic acid are going to go down, and my moles of my formate or my conjugate base are going to go up. But again, how much? Let's get numbers for this. So I'm trying to get to my concentration of formic acid again after this base has been neutralized. So I'm going to take how many moles I started with minus how many moles I have used. That is just 0.25 minus my 0.01. So after this reaction has gone to completion, I only have 0.24 moles of my formic acid left. What is the concentration of this? Well, this is really easy because, again, we have a 1 liter buffer here. So I'm just going to divide by 1 liter, and my concentration is 0.24 molar. Okay, let's continue this calculation because, of course, I need to get my concentration of my conjugate base. So for my conjugate base, my formate ion, I have my initial moles of formate that I had in the buffer, but now I have more because, of course, my formate anion was a product when I added my sodium hydroxide. So I started with my 0.25 moles. I've added 0.01 moles, again, dividing by 1 liter of solution because this buffer is 1 liter. And my concentration of formate is 0.26. Okay, now that I have my concentration of my weak acid and my conjugate base, I can use Henderson-Hasselbalch again. Here is my Henderson-Hasselbalch in generic form. Here it is specific to formic acid. Again, I'm just plugging in my new concentrations here, and I get a pH of 3.77. So this time, this term does not go to 0 because my ratio is no longer exactly 1, it's a little bit off. So you can see how my buffer has resisted the change in pH. Yeah, it's changed a little bit, but not that much. However, I only added 0.01 moles of base. What happens if I add more sodium hydroxide? All right, so this time I'm going to add 8 grams of sodium hydroxide. Again, I want to convert that to moles because we got to do our stoichiometry. So here is my conversion to my moles of sodium hydroxide. I have 0.2 moles of sodium hydroxide. Now, my chemical reaction is still the same. I've added a strong base to solution, so my formic acid is going to come in and neutralize it. And yes, I do need to keep track of how much of my conjugate base I'm going to form, or my formate. So taking my moles of sodium hydroxide, I'm first going to predict how much of my formic acid I have used. So here are my moles of my hydroxide. Using my mole ratio, I'm going to use 0.2 moles of my formic acid. And again, how much of my conjugate base have I formed? Same kind of calculation. Taking my moles of hydroxide, my mole ratio, I am going to form 0.2 moles of formate. Again, it's wonderful that these equations are all 1-to-1. It does make the math so much easier. Just like before, I need to get to concentration of my weak acid and my conjugate base because I need to plug into Henderson-Hasselbalch. But before I can get concentration, I need to know how many moles I have. So for my formic acid, I need to take how many moles I started with plus how many moles I used to neutralize all that base. So I started with 0.25 moles, I used up 0.2 moles, and again, putting this over 1 liter of solution because I have 1 liter of buffer. My new concentration of formic acid is 0.05 molarity. I'm going to do the same kind of calculation for my conjugate base, but of course this time I have formed conjugate base. So I'm going to take my initial moles of my formate plus how many moles I formed. So I started with 0.25 moles. I have formed 0.2 moles. So I'm going to take my 0.45 moles divided by 1 liter solution. Again, this is a 1 liter buffer, and that gives me a concentration of 0.450 molarity. Now that I have concentration of my acid and concentration of my conjugate base, I'm ready for Henderson-Hasselbalch. So again, here's my generic Henderson-Hasselbalch. Here's my specific one. Let's plug our numbers in. Okay, so here are all my numbers, and now I get a pH of 4.69. So you can see that this ratio has changed quite dramatically at this point. This is what we mean by buffer capacity. You only have so many moles of either your weak acid or your weak base in solution. So if you add enough strong acid or strong base, you will overcome that buffer's capacity to keep the pH about the same. Okay, we did a lot of calculations. Let's take a look at a little more organized summary. We started with a 1 liter buffer that had equal concentrations of formic acid and lithium formate. Our pH started at a 3.74, and this is when our ratio of our conjugate base to our weak acid was 1. And we're going to see that having the ratio be 1 is going to be ideal. So initially we just added our 0.40 grams of sodium hydroxide, and our pH changed just a tiny bit. What happened to our ratio? You can see our ratio also just changed a little bit. So if you can keep that ratio close to 1, then you will keep the solution buffered. But what happened when we added a lot of sodium hydroxide, when we added 8 grams of sodium hydroxide? Well, our pH did jump up to 4.69, and look what happened to our ratio. Our ratio went to 9. So the farther away that ratio is from 1, the more your pH will change. This is why generally when we make buffers, we're always going to make them have that 1-to-1 ratio because that gives us the greatest buffer capacity. If you already start with a ratio that's at like 3 or 5, you're not going to have to add that much, either acid or base, to overcome that buffer's capacity. I hope you found this video helpful, and thanks so much for watching.